In the previous lecture, we saw some anomalous configuration of transition elements of developments, and we find that their expected configurations are different from actual configuration, in which we saw about RH 45. Now see the PD 46, whose expected configuration is 4D sup 8 5s sup 2, but actually is 4D sup 10 5s sup 0. And next AG 47, AG sub 47, whose expected configuration is 4D sup 9 5s sup 2, but actually is 4D sup 10 5s sup 1. Now 5D series elements PT 78. Its expected configuration is 4F sup 14 5D sup 8 6S sup 2, but actually is 4F sup 14 5D sup 9 5S sup 1. And AU 79, which expected is 4F sup 14 5D sup 9 6S sup 2, but actually is 4F sup 14 5D sup 10 6S sup 1. Obviously, the actual configurations are obtained by shifting 1 or 2 electrons from ns to n-1 d orbitals. Such type of shiftings in case of some elements like Cr, Cu, Mo, Pd, Ag, Au can be explained on the basis of the concept that half filled or completely filled n-1 d orbitals, as they are more stable than D sup 4, D sup 8 and D sup 9 orbitals. Anomalous configuration of other elements like Nv, Ru, Rh and Pt are explained on the basis of nuclear electronic and interelectronic forces, which discussion is beyond the scope of this lecture. Now let's know the Aufbau principle. So Aufbau is a German word meaning building up. According to this principle, the orbitals are filled up in the order of increasing energy. That is, the orbital with the lowest energy is filled up first, while that of the highest energy filled up in the end. The energy of various orbitals increases in the order given below. 1s is less than 2s is less than 2p is less than 3s is less than 3p, 3p is less than 4s, 4s is less than 3d, 3d is less than 4p, 4p is less than 5s, 5s is less than 4d, 4d is less than 5p, 5p is less than 6s, 6s is less than 4f, 4f is less than 5d, 5d is less than 6p, 6p is less than 7s, 7s is less than 5f, and so on. Now working rule for filling orbitals are given as below. First rule 1. A new electron enters the orbital for which n plus l, that is principal plus azimuthal quantum number, is minimum. Example, if we consider 3d and 4s orbitals, the electrons will first enter 4s orbitals in preference to 3d orbitals, because of the fact that the value of n plus l for 4s orbital is less, 4 plus 0 equals to 4, than that for 3d orbital, 3 plus 2 equals to 5. Rule 2. In case of orbitals for which n plus l values are the same, the new element enters the orbital for which n is minimum. Example, if there is a choice for the electron to enter 3d and 4p orbitals, 3d and 4p orbital, for both of which n plus l values are the same, that is 3 plus 2 equals to 5, comma 4 plus 1 equals to 5, the electrons will prefer to go to 3d orbital because its n value is lower. And above fact is illustrated in below. For example, for n equals to 1, l equals to 0, n plus l equals to 1 plus 0 equals to 1, so orbital will be 1s. If n equals to 2, L equals to 0, n plus L, 2 plus 0 equals to 2 or vital 2s, n equals to 2, L equals to 1, n plus L, 2 plus 1 equals to 3 or vital will be 2p. For n equals to 3, L equals to 0, n plus L, 3 plus 0 equals to 3 or vital 3s. N equals to 3, L equals to 1, n plus L, 3 plus 1 equal to 4 or vital 3p. N equals to 3, L equals to 2, n plus L, 3 plus 2 equal to 5 or vital 3d. N equals to 4, L equals to 0, 4 plus 0 is equal to 4 or vital 4s. N equals to 4, L equals to 1, n plus L, 4 plus 1 equal to 5 or vital 4p and so on. So according to rule 1, the electron occupy 1s because the value of 1s is 1s, that is n plus L is less than 2s. Similarly, next electrons occupy 2p, the value of n plus L for 2p and 3s is the same. Hence, according to rule 2, the electrons occupy the lower value of n. Hence, electrons occupy 2p, then they occupy 3s. In this way, the different orbitals are filled up with electrons. The relative stability of various orbitals and sequence in which the electrons occupy the various orbitals are as follows. So, electron will go first in 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, then 5d, then 6p, then 7d, then 5f, then 6d, and then 7p. Example, in the case of potassium, atomic number 19, the 19th electron might enter 3d or 4s subcells. The working rule for this is that the electron will enter the subcells having a lower value of n plus L. So for 3d, n equals 3 and L equal to 2, and therefore n plus L, 3 plus 2 equals to 5. And for 4s, n equals to 4 and L equals to 0, and therefore n plus L equals to 4 plus 0 equal to 4. Hence, the electron will enter the 4s subcell in preference to 3d. Now, exceptions to the Aufbau principle. First, a single 5d electron is added before any 4f orbital is occupied. Hence, n plus L equals to 7. In both the cases, the electron must occupy 4f orbital. After that, the remaining 9 5d electrons enter this subcell after the 4f subcell has been completely filled with electrons. Similar is the case with 6d and 5f. The electron must occupy 5f orbital, but actually 1 or 2 electrons go to 6d orbitals. This is based on the fact that 4f and 5d subcells of energy are very close to each other, and 5 and 6d subcells are even still closer. Example, lanthanum La, atomic number 57, and its configuration will be 1s sub 2, 2s sub 2, 2p sub 6, 3s sub 2, 3p sub 6, 3d sub 10, 4s sub 2, 4p sub 6, 4d sub 10, 4s sub 2, 5p sub 6, 6s sub 2, 4f sub 0, and 5d sub 1.